Hello, everyone. I will be recording this class since we won't be able to meet face to face this week. And also, I hope that this will give you some extra time to go over the notes and process what we're talking about in here. So today's topic is transport mechanisms through pores. I'll be giving some basic, very basic information in addition to some up-to-date papers who had used these basic information for their own use. So we start this discussion by talking about Fick's law. We can broadly classify transport in solids into two types of diffusion. Diffusion that can be considered to follow Fick's law doesn't primarily depend on the actual structure of the solid, and diffusion in porous solids where the actual structure and the void channels are important. So just from here, just from these two bullets, we can think that we're going to be talking about this Fick's law, and then we're going to make some corrections to understand what's really happening in porous solids to what we had learned at this step. So Fick's law is the type of diffusion in solids that doesn't depend on the actual structure of the solid. Okay, solid diffusing is actually dissolved in the solid to form more or less homogeneous solution. That's our basic assumption here. And when we're talking about these kinds of processes, what we're talking is actually what we call flux. And flux is a positive value. It's the number of particles passing from a unit surface area per unit time. For example, if we have a slab of wall like this, okay, and if my molecules are transferring from here to here, this is the area that all these molecules are transferring from concentration C1 to C2. And when we try to model this fact, we use this Fick's law. But this can be applied to all sorts of mass, heat, and momentum transfers, okay? So for mass transfer, for heat transfer, or for momentum transfer, we say that rate, we have to define the rate of a transfer process. And here this is mass or heat or momentum. And we're going to be fixing our discussion onto mass because we're transferring mass from one phase to another. Is we need a driving force here, driving force over some resistance, okay? So let me try to delete this and resistance, okay? So our resistance is the thickness, delta Z is the thickness of our slab, of our wall, and driving force is can change as a function of what we're transferring, mass or heat or momentum. And when we try to sort of write what's going on in here is, in general, if this can be described as flux, okay, and it's a negative term, which is important, and this is my transport property, okay, and this depends on, this is my thickness, and this is the transferred fact, whatever we're transferring, mass, heat, momentum, whatever, okay, and this is my transferred property. That's we're going to be a lot talking about this, how that is changing as a function of mass, for example. So for example, momentum, it becomes Newton's equation for momentum transfer. For heat, it becomes Fourier's law for heat of conduction, or for mass, it becomes Fick's law for mass transfer. Okay, so Fick's law Fick's law of molecular diffusion. Okay, diffusion. We assume that we have a stable phase that's full of molecules A, okay? And then I have molecule B, it can be a gaseous molecule. It's trying to travel from here to here to here to here through stagnant A molecules, okay? So this is called Fick's law for binary mixtures, okay? And when we look at this equation here, this is the most general form, for molecular diffusion, it becomes flux of A, this is my molecule A, is trying to diffuse through B, is minus because, why? Minus because it's always traveling from a high concentration to low concentration, and it's always C2 minus C1, so it always becomes a negative term. It's DAB, A diffusing in stagnant B, DCA is the concentration difference. That is my driving force, right? Because one concentration, the concentration of this is less than this is more here or less here. So there is a concentration driving force through a certain resistance. That's the thickness of whatever medium it's trying to dissolve through. Okay, and so this is my concentration here, which can be written as, this is the concentration of A, so JA can be also written as minus total concentration, DAB, dXA over dZ, okay? And then, I don't know if I can insert template. Yes, I can do that. So what did I say? JA is equal to minus CDAB dXA over dZ. And if I were to integrate these things, okay, through certain thicknesses and certain concentrations, well, for CA, or let's say this is CA, okay, JA becomes DAB CA1 minus CA2 over Z2 minus Z1. So this is the very basic Fick's law for molecular diffusion. But when a molecule is traveling from one spot to another, and let's say we have molecules here, and my blue molecule A is trying to diffuse, okay, through here, we assume that this is not moving. But indeed, this has some velocity, but indeed it has two factors, okay, two things that are involved in this movement. And that's the first one is the diffusion that we already talked about. So this is diffusing through this. But also, if this is moving as well, then we have to consider that. That's called the bulk diffusion. So this is one diffusion, and this is not bulk movement, let's say, okay? So we say that the total rate of A, that is the total flux, okay, total flux of A is equal to JA, which I already derived, plus the total bulk movement, okay, concentration times the velocity of my molecule. So Na is known to be JA plus Ca over C, Na plus Nb, because I have two molecules. It's binary diffusion. So in general, if I were to write the whole thing by starting from zero, the whole derivation, we already saw how we derived this part of this equation. This is, okay, this is my molecular diffusion, and this is my bulk diffusion, Na plus Nb, okay? With that, I'll try to continue with the class notes. Okay, so this is just a slide number 2. This is a given fact, and I try to tell you where this whole thing is coming from. For binary diffusion, this is my Z1, Z2, this is A, trying to diffuse through my slab, and CA1, CA2, CA1 is higher than CA2. For the bulk flow term, usually this part is very small, since XA is usually very, very small. And so usually we consider just this diffusion term, minus CdAB dXA over dZ. And if this is, for example, diffusion through a solid slab, this is Z2 minus Z1, but this can be done for example, through a cylindrical wall. For example, you have some nanofibers or something that's diffusing through the cylindrical wall, and then the unit area changes with the surface area of whatever is trying to diffuse through. So it makes a difference as a function of what is trying to diffuse through from. So these things can be given as examples for example, hydrogen diffusing through a membrane, or a polyethylene film being used for packaging a pharmaceutical product, and so on. Okay, so let's keep this in mind. This is a very, very basic generalized formula for all sorts of diffusion. Okay, but when we consider transport mechanisms through pores, and that's what we're trying to come to, right? Because we're trying to diffuse things through nanopores. That's the whole purpose of what we are using these nanopores for. Before, we used Fick's law and treated the solid as a uniform homogeneous-like material with experimental diffusivity, DAB. These can be theoretically found, or they can be measured. But now we are concerned with porous solids that have pores or interconnected voids in that solid that affect diffusion. Okay, so we have a porous structure here that affects the whole diffusion phenomena. Okay, and so we have to put some corrections. Okay, in general, what did we say? Na is equal to DAB dCA over dZ, and we, as you can see, we have two very basic things that we had added while we are considering these nanopores. That's the open void fraction, because the more open it is, the more it's going to travel from one spot to another. Okay, so this is linearly related to the open void fraction, but it's inversely related to the tortuosity factor. That's called the tortuosity factor. Corrects for the path longer than Z2 minus Z1. So it doesn't just go from here to here like this. It goes through a very tortuous path. So we make some corrections by adding these two terms for what's happening in the pores. Okay, that's the point. It's an example of a very typical, just to make things more solid to you. A sintered solid of silica, 2 millimeters thick, is porous with a void fraction, tortuosity. The pores are filled with water. At one phase, the concentration of KCl is held at something. It flows rapidly past the other phase. Calculate the diffusion. Okay, so you can do that by just plugging in the numbers that are given to you, and these are usually very well-known terms. So diffusion of gases in porous solids can also be considered by thinking of this equation in here. That's the by considering the PV and RT, you can write the number of moles in terms of P over RT, and you will come up with this formula here. Okay, and it's usually how much my effective diffusivity, the real one, deviates from what is happening in a homogeneous medium, is a function of, E over tortuosity. Okay, so this porous media of beds of glass, fair sand, salt, talc, all of these things become a function of what's really happening in my porous media. Okay, and for example, a very typical example was given by these people who had written this paper on the transport in nanoporous materials, including MOFs, metal organic frameworks, that we will learn. The applicability of Fick's law, for example. So just this paper, for example, discusses how much of what's happening in a nanoporous material for transport, including MOFs, how much of this is applicable for when we consider Fick's law. Okay, so for example, they say diffusion in nanoporous host gas systems is often considered to be too complicated to comply with such simple relationships as Fick's first and second law of diffusion. However, it's shown here in that the microscopic techniques of diffusion measurement, which they measured by some NMR techniques, provide direct experimental evidence of the applicability of Fick's law to such systems. Okay, this means true in many situations. This remains true in many situations, even when the detailed mechanism is complex. So this is a very important topic to have a general understanding again for Fick's law and how to consider things that deviate from it and how difficult it is or not. Mass transfer in nanoporous materials cannot always be assumed to follow simple laws of ordinary diffusion, which I've tried to derive for you. Deviations from Fickian behavior are to be expected if, during the observation time, there is no fast exchange between states of different mobility. Such behavior may be encountered in the hierarchical pore systems with limited exchange between the micro and meso or macro pores. Okay, so things become a little complicated when the hierarchical pore systems are involved, but this is the basics of this whole thing. Another example was given by these people who had written this paper on migration model of silver-loaded zeolite in antibacterial kraft paper, which is a big deal, as I had already talked to you about in my first class, because you load silver into some porous matrix, but then you have to consider the release of it, where it's used. For example, it's used in a kraft paper in here, so you have to think about the whole diffusivity of the silver in zeolite into kraft paper and so on. So again, in your abstract, once you were to look at a paper like this, you can see that they say, based on the Fick's law, model about the migration of silver-loaded zeolite on antibacterial kraft paper was built, and migration of antibacterial agents, this silver, blah, blah, ethanol, this much acetic acid were detected by AAS. This is, they measure the elemental composition of what is being released experimentally, and based on the Fick's law, which we had learned, they come up with this whole model of what's happening in the depths of the paper for the antibacterial agent. Okay, with that, I would normally give a short break and make you think about what's happening here. And with that, I would like to start to talk about the mean free path. So now we have this broad understanding of Fick's law. Our molecule is entering the pores. Let's say this is our pore. This is my molecule here. And that's what's happening. We have a resistance, we have this and that, we have diffusivity, and stuff like that. But what's this molecule is really doing in the pores? What are the possible mechanisms that it could follow? And when we start to consider what's really this thing is doing in my pore, we have to always think about the mean free path. In order to consider diffusion, we must first look into the details at molecular collisions. Okay, we suppose that all molecules are the same, collide elastically, and also suppose this to be an effective molecular diameter. So what's important here are two things. Number one, how big is my molecule, and how big is my pore? What's it called? The pore diameter. Okay, pore diameter, for example. Pore diameter and how big is my molecule. You have to always think about what you're trying to put into this porous system? Will it fit or not? How many collisions it's going to do? And there is a huge amount of research going on in modeling these kinds of phenomena. Okay, however, why is this important? Because of this, the sentence here. Okay. However, the pores are often too small in diameter, and the mechanism of diffusion is basically changed. Okay, the pores are too small that the molecule can't just, you know, follow a route. It starts hitting the pores, the pore walls, and so that's why the mean free parameter, the mean free path is important. It usually occurs in heterogeneous catalysis where gases diffuse through very small pores to react on the surface of a catalyst, and the diffusion of gases may depend upon the diameter of the pores, which I told you about. So we first define a mean free path. Okay, I'm not going to make a derivation for this, you're lucky, but this is, you know, this is, let's say this is mean free path. Okay, there's a viscosity term, and there are all these terms that depends on what we're trying to put into our porous network of this gas molecule or whatever, which is the average distance a gas molecule travels before it collides with another gas molecule. Okay, so this definition here is important. I'm going to try to highlight this, okay, which is the average distance a gas molecule travels before it collides with another gas molecule. Okay, we only consider here the simplest approach. In reality, other molecules will move too, of course. We always consider the simplest approach. And this paper I had already put into auto class. I believe this is a very, very good review paper explaining everything that's possible to be explained in diffusion and nanopores. And you know, as I already told you in the very first slide of this presentation, we always think about how does things deviate from bulk. So we first define things for bulk systems, like I just did, the derivation or whatever, the understanding. And then we say as nanotechnology people how much it deviates from the simplest approach. So the term nanopores is increasingly used for pores that are smaller than 100 nanometer. As the term nano implies properties different from single molecules and the bulk, the term nanopore might be most useful in the context of describing phenomena in pores that even qualitatively deviate from those expected in the bulk. Okay, that's why I highlighted the central. We look at the deviation. And then we try to evaluate the overall effective diffusivity. This is called the effective diffusivity to account for the porosity and the pore network of the structure. And there are all these amazing papers and research that considers different pore networks, pore structures. I mean, you can imagine like Legos, how many different millions of possible network connections and porous natures that can be created. That's going to give you what you want at the end of this path. Okay, you want this molecule to pass, you don't want this molecule to pass, and you try to change these connectivities. That's going to allow this molecule and block this molecule, for example. Okay, so that's why these theoretical studies become a big deal at some point. So while fundamentally dissimilar from diffusion in micropores, there are nevertheless mechanistic differences to diffusion in the bulk as well due to the presence of the enclosing mesopore walls. Okay, so this slide and this figure tells you three things. This is my porous wall, okay, and you can see three mechanisms here. There is something called Knudsen diffusion, there's something called surface diffusion, and there's something called molecular diffusion. Molecular diffusion, as you can see, is your molecule is small and it's traveling without hitting the walls. This can happen. Or you can have such a big molecule that it usually hits the walls before it goes and hits another molecule. Okay, it usually hits the walls. It's bigger and my pore is smaller that it hits the wall. So its mean free path, I mean, then we're going to come back to this mean free path for Knudsen diffusion is high. And there's surface diffusion, it travels through the surface, okay? For example, this is severely confined molecular transport. And then this figure is important, and I'm going to give another figure of this in the coming slides. But this, as you can see, shows you the how things are traveling as a function of this is pore diameter, and this is the transfer of that molecule through the pore. Okay, so let's have a look at this from a closer point of view. This figure, we are seeing that there are different diffusion mechanisms in a porous medium. Not everything is following Fick's law, not everything is perfect in our little worlds. There are these tortuous paths that we have to go through. Okay, so the total flux J is described as the sum of diffusive, Knudsen and molecular flux, and the surface flux as follows. Okay, they say okay, but even if you don't have to memorize anything, you have to see that what we had as J before now has some different terms. It has some JD, whatever is called JD. This is the Knudsen and molecular, and there is some viscous flow. Okay, maybe that's called the bulk flow, and some surface flow. So there are these different flow mechanisms that are happening in my porous network, and they did an equivalent network of resistances that they used to evaluate the total flux here. And so they said that these things act like as if this acts like you are trying to transfer like electrons through a wire. They face different resistances, and these are my resistances. These C molecular and Knudsen act series, but they act parallel to like convective and surface fluxes, for example. So this is as if we are trying to transfer some electronic property from my porous network one side to another side. In a unique nano-confinement phenomenon occurs, and it's called Knudsen diffusion. Okay, this is very important term. Okay, Knudsen diffusion. I'm going to ask about this. Knudsen diffusion. When the mean free path of a gas molecule becomes larger or is of the same order of magnitude as the local channel diameter, the frequency of the collisions between the molecules and the walls exceeds the intermolecular collision frequency. So this is my intermolecular collision frequency, and this is my Knudsen diffusion. Okay, when this is too big and my pore diameter is too small, the mean free path of my gas molecule becomes larger or the same order of magnitude with my local channel diameter, that the frequency of the collisions between the molecules and the walls increase. Okay, that's what happens when the Knudsen term, this term is higher than the rest. Okay, so you have all these terms, and at some point you have to think, okay, at this point this is higher, these can be negligible, and so on. Okay, this is how people are trying to solve what's happening in their systems. So Knudsen diffusion, again, it's important for liquids, since this mean free path is too small, diffusion follow Fick's law. Okay, right, we learned about this, we listened a lot about it. Okay, we derived it and everything. The relative value of the mean free path compared to the pore diameter varies, and number one case becomes the Knudsen diffusion of gases. A gas molecule A at partial pressure PA1 at the entrance to a capillary is diffusing through the capillary having a diameter d. Okay, the pores network can be thought as a capillary. The mean free path is large compared to my diameter, and as a result, the molecule collides with the wall, and molecule-wall collisions become important. Okay, and that's when you see that this is what's happening. This, you can say that okay, the diffusivity of Knudsen diffusivity of my molecule A can be found from this equation. Okay, from this equation, and you use that to figure out what your diffusivity is in your network, for example. Okay, so when K, the number K Knudsen is higher than 10, approximately. The diffusion is primarily Knudsen. The diffusion of A for Knudsen diffusion is completely independent of B, okay, because it doesn't see B. The molecule B is also in my pore. These are A's and B's. They're trying to diffuse. This is my B, and this is my A. But this A is too big, and this B is too small, that this follows maybe molecular collision, but my molecule A is hitting the walls. It cannot control itself. It hits the walls before it hits another molecule. Okay, so A collides with the walls of the pore and not with B. That's what it means. Okay, so this can be followed. This is like this is as if there's no B. Okay, and as the Knudsen number gets larger, the error decreases since the diffusion approaches the Knudsen type. So what do we need to have for Knudsen? What we need is to increase mean free path. Okay, and this is the other way around. This is the molecular diffusion. This is the Knudsen diffusion. Okay, this is not hitting the walls. It's simply traveling in my channel, in my capillary without hitting the walls. And then this is followed. So this is what happens with the Knudsen, let's say, which we already derived. And this is what happens when the molecule is following the molecular diffusion path. If diffusivity is equimolar, the equation becomes Fick's law. So everything becomes okay for us to follow the Fick's law in that case. Okay, and of course things are not usually black or white. We usually have to face some transition region diffusions where it both hits and not hit the wall. So when the mean free path and the pore diameter are intermediate in size between the two limits given for Knudsen and molecular diffusion, transition type occurs. Okay, and then there are these other corrections and other equations that are inserted into our original equation, where it allows you to guess what my flux is in my porous network. So these Knudsen molecular and transition region diffusion mechanisms are important in the sense that, for example, if you look at the effect of total pressure on the diffusion flux of A in the transition region, for example, as the pressure increases, as the number of molecules increases, for example, it first follows the Knudsen diffusion, and after a transition here, the molecules are too much in my capillary. Okay, so first it hits the walls. It's Knudsen. Okay, Knudsen, let's say, and then the molecules becomes too much that it stops hitting the wall. It has to like hit one molecule to another, so it becomes molecular diffusion. And that's why this graph is important. You have to figure out at which path you are following as a function of your number of molecules and so on. Okay, but these are the three major mechanisms that are followed in a porous system. And if you look at the summary and significance, actually the pores are not straight and cylindrical, but irregular. Equations for differences in pores must be modified for actual porous solids. The pore diameter vary, and the Knudsen diffusion is a function of pore diameter. Okay, adding tortuosity factors and the void fractions, we learned to come up with this flux equation here. And it's usually a matter of how much we are deviating from the bulk, which usually again is a function of how close you are to Knudsen diffusion, which is a function of this diameter and of the void fraction. Okay, and people had done a lot of experiments to figure out that this actually is a function of this and this, which I will upload the paper for that measurement as well. So gas transport through a porous material is of importance in many applications, including design and analysis of gas electrodes. In particular, it's often necessary to calculate the flux of gas diffusing through the material, and this depends on the internal microstructure of the pores. Because of the solid portions through which in general there is no diffusion, the gas diffusion rates through porous materials can be significantly lower than through air, depending on porosity, pore size, pore connections. Okay, so I think I had shown you enough to show that these are a function of these things. Usually the effective diffusion coefficient is correlated to the corresponding coefficient through air and the porosity. Okay, and this is what that equation is all about. And this, I'm going to upload the paper on this, where they had actually really measured that this effective diffusivity for a changing porosity is actually following this behavior. Okay, so K, dm represents the effect of pore diameter on diffusion, which we refer to as Knudsen factor, and this represents the dependence of effective diffusivity to diffusivity in air and on porosity. Okay, and these are some, for example, this is a very good review article published this year in 2021, connecting theory and simulation with experiment for the study of diffusion in nanoporous solids. Okay, so they tried to come up with some calculations of diffusivities for different nanoporous, MOFs, macroporous, microporous materials. Knowing what we had learned for this fixed law of everything, they tried to theoretically calculate these diffusivities for different nanoporous solids. Okay, and what's important again here is, for example, there are some people who were the first ones to perform a molecular dynamics simulation where the trajectories of individual particles are tracked. So they track these individual particles and see what they're really doing in these porous networks over time by integrating the Newtonian equations of motion from the interatomic forces of individual molecules over time. With increasing computational resources, tremendous methodological advances and more accurate descriptions of molecular interaction simulations have moved from simple model systems to increasingly accurate models of real physical systems. So this paper, I mean, I read the whole thing that I highlighted, but what it's trying to do is they are summarizing which model is good for which system. Okay, what type of nanoporous material, which model can be used, and they gave an amazing review on what's really happening in these systems. And the figures I had shown you about the resistances is taken from this review paper. And this was an important deal because of, for these people, this MTO process, the methanol to olefin is a very important process in the chemical industry. Okay, and this whole thing, the methanol to olefin process, is controlled by this diffusion and flux and what's happening in there. Okay, so the correct how to say calculation of this diffusivity is a very big deal to understand, to optimize what's happening in our MTO process for that purpose. So, for example, they said that the Newtonian equations can be integrated numerically using a variety of different integration schemes. And then they, this is their equation one in this review. And this paper is like a 60-page paper. This is the equation 1. And but what they're trying to do here is, like I said, they're trying to calculate the self-diffusion coefficients for all species I. Okay, this is my diffusion coefficient, is calculated from the mean square displacement, that's called the MSD, of adsorbates over time using Einstein relationship. And this is my relationship, okay? And what they're doing is they are literally measuring the time for a single molecule to travel from spot 1 to spot 2. Okay. Okay, and then D is the dimensionality of the system, N is the number of adsorbates. The self-diffusion coefficient can be calculated from the slope of this MSD versus time. Okay, they measure it, and then they plot it, and then they simplify the self-diffusion coefficients by that. In porous media, there also exists a subdiffuser region and all these different regions that we're not going to go into details. But what was summarized in this review paper, and I'm going to go through this in our live session next week, in this paper was used actually in another paper that we already talked in our live session last week on the shape selective diffusion of olefins in 8-ring solid acid microporous solids, for example. Okay, and again they say the diffusion of olefins through 8-ring solids was done by molecular dynamics simulation using a newly developed flexible force field in the context of methanol to olefin process. Again, it's a big deal. They wanted to change these number of connections. They use different nanoporous materials, alpos, suppos, zeolites, different topologies, different acidities, different temperatures, compositions, everything, and they calculated how effective diffusivity is changing as a function of all these different nanoporous connections. So that was a very good paper. These are the different ring structures that they had used. They gave a summary of what they look like, the ring topologies, this is suppose, and then these are the acidic forms of these materials, okay? And there is a good methodology that they summarized here, which we'll talk about in our live session to make you feel a little bit more familiar with these things. And then as you can see, this different research group had used this approach to measure their diffusion coefficients. Okay, so this is just to show you that there are these approaches that are used to measure these diffusion coefficients. Okay, and when they are doing that, this is what they simulate. This is my molecule that travels from here to here to here as a function of time, elapsed time. Ethene is traveling, and then at the end, they come up with these slopes that I told you here. The self-diffusion coefficient can be calculated from the slope of MSD versus time, and this is what it looks like at the end. This is time, and this is the MSD result for different frameworks. So this is a very, very good, genius way to measure these self-diffusivities. And when you look at this figure, what do you see? There are different temperatures, how they act for ethene. But as you see for propene, things start to not follow a linear slope. That means that propene is not following what they're using in here. And so they actually omit to work with propene, and they've continue their research of theoretical calculations with ethene, because this molecule is not following this route. And then they write their conclusion according to what they had found. But this was another good table, ethene diffusion coefficients at 3 temperatures by fitting to MSD curves. Okay, and these are my diffusivities for different frameworks, different topologies. These are the acidic forms of these molecules, which we will learn in our class. And so if you were to look at the conclusion in this paper, we investigated the diffusion of ethene and propene in a series of 8-ring zeolites to assess the influence of topology, acidity, flexibility on the diffusion in confined zeolites and zeolite materials. So this was a very, very good paper to follow for those who are interested in at least who intend to understand a little bit of diffusivities, behaviors in different frameworks, okay? Because it's hard, very, very hard to make an actual experiment who can really make these measurements. Okay, with that, I would like to conclude my recording, and I hope that it will help you to understand these concepts before our live class in our coming